Hello there, this is MJ on the journey back to Silicon Valley. Today we're going to be looking at problem 53 on LeetCode, maximum subarray. So given an integer array nums, find the subarray that has the largest sum. So the first thing I didn't understand is what does, so I looked up what a subarray is, and it has the word contiguous, and I couldn't figure out what that was. So basically, contiguous refers to data that is stored in a continuous block of memory. So in other words, an uninterrupted sequence of elements in an array. That's what a subarray is. Okay, so my initial thoughts to actually solve this solution was to figure out all the subarray possibilities from the input array. So finding out all the possible subarrays, and then using a two-pointer, current and next, and then on each iteration moving the last element of the array to the left. So decreasing the size with each iteration, and then updating current and next accordingly. As I started to actually implement this, it started to feel like it's flawed, because on each iteration I'm moving the last element of the array to the right. So I thought, if I'm doing that, then I need probably 3 pointers to also keep track of the last item. And then it hit me that probably I need to rethink the whole approach. I don't know if there's even such a thing as a 3-pointer. Well, you can implement it, but I don't know if that was ever used, or it felt wrong. So I rethought about the problem, and then I decided to actually iterate over the input array and then slice all possible subarrays, and then store them in a hash map, store the subarray sum as the key, and the subarray itself as the value. And then go through the hash map and then return the highest key as the solution. And here are the steps. So initialize an empty hash map, calling it sum map. Iterate through the array once using I, and then a second time using j. So we're going to go through all the elements, but for each element we're going to create a subarray that starts at index I and end at index j plus 1. And the idea here being is I is going to represent the beginning of the array, and then j plus 1 will represent all possible endings of the array. And using the reduce JavaScript built-in function, we're going to get the sum of the subarray we are at, and then we will add the sum to the hash map as the key, and then add the subarray itself as the value. And then iterate through the hash map and get the max key and return that as the solution. And this is the code right here. So it's executing the steps I've just went through here. A couple of things to note: maybe JavaScript built-in functions slice and also reduce, and then using the object.keys and reduce again to find the max. Math.max obviously finds the max between whatever parameters you feed it. And this solution was accepted on LeetCode, passed all 3 test cases. However, when I submitted the solution, I got a runtime error, as you can see here. So I've done some debugging, and I realized actually that what is happening is a memory allocation failure. that is caused by the sum map object, because on each iteration there's a key and value pair that is being added to the object, and it's increasing its size with each iteration until actually the whole heap space is actually exhausted, and that's why I'm getting this runtime error. So, but looking at the solution again, I realized that it not only creates a lot of memory, it has O of n square memory complexity, but it also has O of n square time complexity, because it iterates through the entire array, and then for each element it creates a subarray. So it has O of n square both in memory and time complexity. So after a few searches, I discovered the kadane algorithm. And the approach is basically initializing two variables, one to keep track of the current sum, and another one to keep track of the max sum that was seen in the array so far. And then iterating over the array and updating the current sum and the max sum accordingly, and eventually returning the max sum as the solution. And here are the steps. So initialize two variables, current sum and max sum. And both of them are going to be initialized to the first element in the array. So both of them will start at nums 0. So we're going to start a loop starting at index 1 and then ending at the last element of the array. No, I'm currently blanking out here. No, actually, okay. So on each iteration, we update the current sum by taking the maximum between two values, the current element and the current element plus the current sum. If the current element is bigger, that means it alone is a bigger number than the current sum. So it's better to start a subarray at the current element because it's already bigger. And if it's not, we just extend the array that we have. And then we update the max sum by choosing the maximum number between the previous max sum and then the current sum. If the current sum is bigger, then we update the max sum to reflect that. And then once the loop is done, we're returning the max sum as the solution. And here's the code for that here. So it's implementing the steps I've just read right now. A couple of things to note again. Math.max just returns the max of two comparisons. And then, yeah, nothing else to note. Current sum and max sum are initialized to the beginning of the array. And yeah, so I ran this code. The solution passed all three test cases on LeetCode. And when I submitted the code, here are the stats. So it's beating 54% of all submissions on LeetCode for runtime and 32% for memory. So this solution has a linear complexity because we're only using a single for loop to iterate over the array once. And then it has constant memory complexity because we're only creating two variables, current sum and then max sum. It's one thing that's worth to note is that the initial brute force solution allows for not only finding the sum, the subarray sum, but it allows for finding the subarray itself, which is not the case for the kadane algorithm. It just returns the sum. But let's say you wanted to know or needed the actual subarray that the sum came from, you won't be able to do it with the kadane algorithm. But with the brute force approach, you can. So that's a little bit of credit there to brute force. So the kadane algorithm seems to be the most optimal solution for this problem in terms of both time and memory complexity. However, for very large arrays or inputs, the time complexity can be improved to big O n of log n by using a divide and conquer approach, because the logarithmic growth rate tends to slow down as the input grows. So the logarithmic growth rate is slower than the linear growth rate. So if you have very large inputs, using a divide and conquer approach will improve time complexity. And here's what the solution looks like. It's pretty convoluted, and it's not the most straightforward of solutions, but it is the optimal one if you have very large inputs. Now, I must confess, I have not yet taken the time to understand this solution, nor how to implement a divide and conquer algorithm appropriately. But I decided to stop here and leave that for homework for later, because I've spent quite a bit of time on this problem. Now, a couple of things here. The what you see on the screen is a detailed article about my thought process and the steps that I went through to actually solve this problem. It is available on my blog and also on Medium, and the source code for the optimal solution using the kadane algorithm is available on Github. And both the link to the source code and the blog and Medium article are going to be available in the description of the video. If you found this useful, I hope you did. Go ahead and hit the thumbs up and also subscribe. And until next time, this is MJ on the journey back to Silicon Valley.